Okay, 8.1 is on set theory. So first off, what is a set? Well, a set is just a collection of, in fact, a better word, I'll say things. We refer to these things as elements. Now, these elements can be anything. They can be people, colors, countries, languages, but for purposes of our class, we'll just consider the sets that are a collection of numbers, the elements being various numbers. Oftentimes, a set will be notated as a list split up by commas, surrounded by curly brackets. So here's a quick example of what a set could look like. This is the set containing the numbers 1, 2, and 3. Before we talk about finite sets, sets with a set finite number of elements, let's talk about some infinite sets because we've been using them for years already. The first infinite set we're going to consider is the set of integers. So the symbol we use for integers is this z that has two lines there in the middle. And the integers, as we've talked about before, are all positive and negative numbers and 0 without decimals or fractions. So I could also notate this with an ellipsis, getting the negative side, going through 0 to the positive side. We'll also consider the positive integers, which is this z with a little plus above it, and that's the positive integers. So the integers starting at 1 and going to the right, greater than or equal to 1. Do note 0 is not a positive number. 0 is neither positive nor negative, so it's not included in the positive integers. We also have the natural numbers. The natural numbers will notate as this n with 2 bars down the middle. And for purposes of our class, we'll let the natural numbers be the integers greater than or equal to 0. Depending on the reference you're using, they may or may not include 0 as a natural number. For our class, we will. For later classes, if you start talking about natural numbers, make sure that they either do or do not include 0 in there before you start making assumptions about it. So these are all the numbers with no decimals, no fractions. We can add on to those the rational numbers. The rational numbers are, we usually consider them as fractions. We use a Q with 2 bars there to represent them, and we don't have a good way yet to notate that. We'll see one in 2 more slides, but we know it's basically the set of all things that can be written as a ratio of 2 integers, the second integer not being 0. So we'll have a cleaner way to write that shortly. Next we have the real numbers. And the real numbers are the numbers that we've used almost exclusively throughout elementary school and high school. It's basically any number that we can sort of put on a number line, including the integers, as well as anything sort of between the integers. If it's one-dimensional, real numbers can cover that. And then the final thing we have is the complex numbers. and we spoke a little bit about them when we were dealing with quadratics. That's a good sort of way to introduce complex numbers, and that can be written as this C with a little extra bar. And so these are all sets of numbers. They are a collection of numbers, and they're all infinite because they have infinitely many numbers in each set. Now, what might be a little bit easier to consider is finite sets, a set that has a finite number of elements. And there are many ways. They're actually very easy to represent. So here are just a few examples. So one example is, let's say, the set of single-digit positive integers. So I'll use a capital A. Capital letters are how we would represent sets. And the set of positive single-digit integers would be something like this, the set of 1, 2, 3, 4, 5, 6, 7, 8, and 9. Another example would be the set of prime numbers between 10 and 30. So that could be 11, 13, 15 is not prime, neither is 12 and 14 for that matter. 17 is prime, 19 is prime, 23 is prime, and 29 is prime. So these are all the prime numbers between 10 and 30. Or I could also consider the set of all even natural numbers less than 100. So the smallest even natural number is 0. And we keep on going even numbers. There will be too many to write out explicitly, so I'll use this little ellipsis to say, okay, I'm skipping some stuff, but it doesn't go on forever, so I'll stop showing 94, 96, and the last even natural number less than 100 is 98. I said less than, strictly less than, not less than or equal to. So these are some examples of finite sets, and they are finite because they have a finite number of elements. So I can actually count the number of elements in this way. This is how I would show the number of elements in a set. So the number of elements in A, number of elements in A like that, is going to be 9 elements. The number of elements in set B is going to be 6. The number of elements in set C is going to be 50 if I were to count them all. And these are finite. Just to sort of wrap things up, this number of elements can be used for infinite sets as well. So, for instance, the number of elements in the integers is infinity. We also have sort of a special set called the empty set, which is the set with no elements and that can be written as either sort of the curly brackets with nothing in there, or as this circle with the cross through. You might be used to seeing that notation as no solution. It's actually used because it's showing that the set of solutions is empty. There's nothing in there. And if the set's empty, then we know that the number of elements in that set will be 0. Now, it is definitely worth noting, this is the empty set. There are no elements. The set containing 0 is not the same as the empty set. This set has one element. That element is 0. This set has no elements in it. Sometimes we want to build sets, especially infinite sets. They can be harder to just sort of notate. We talked about the rational numbers. So in order to build sets, there are two symbols and some sort of terminology putting together symbols that we can use. The first symbol we'll often use is what's called is an element of. Okay. You could also use the word in. Something is in. And that symbol is this little E-looking thing. And the way that works is this. If I say x, this little e, and then this z, this means x is an element of the integers. This implies, so if x is an element of integers, then x can be numbers like 2, -37, 5,678, these things. X cannot be anything that's not an integer, so 1.5, -pi, square root of 2. X can't be these, so x is an element of the integers, means that x is one of them. It doesn't tell me which one it is, but it is somewhere in this set. We also have the useful sort of term such that. And that's written with a little vertical line. Now the best way to sort of explain this one is through a full example. So let's consider the rational numbers again. So we have our Q for quotient. The rational numbers are the set, so I use my set notation, of all P over Q such that, and this is very specific, P and Q are elements of the integers, with one additional thing. There's a restriction on what P and Q can be. Q cannot equal 0. So this is just one example of how to use set builder notation. There are many ways that this can be done. So, for instance, I could make a random set. Let's just say, okay, what about the set of all points, x, y, coordinates on the plane? Well, I could do it like this. Set of all x, y, such that, so we have the coordinates, and if they're on the plane, then x and y could be natural numbers, integers, positive integers, real numbers, but they can't be complex numbers or else they wouldn't be on the plane. So the set of all ordered pairs x and y such that x and y are elements of the real numbers. Or I could do something, for instance, I could say, okay, what are the first 10 positive perfect squares? Well, those would look like this. I could say, okay, let's make x squared such that x is in, and I could try to do something weird with that z here, or I could just make it easy. 1, 2, all the way up to 10. And then I'll have... Now, this is a little bit silly because I've just written out 10 things. I could have written that set out explicitly as 1 squared being 1, 2 squared being 4, 3 squared being 9, all the way up. Let's see, 8 squared, 60. To 100. So this didn't really save us any room, but for a lot of these infinite things, there's really no better way to do it. Now, I guess it's worth noting, and I'll make sure it's in the notes, there's no specific order to these sets. I listed this one in increasing order, but the set starting with 100 and ending with 1 is the exact same as the set starting with 1 and ending with 100. It doesn't matter. The set is orderless, where these curly brackets mean no order. These parentheses require order. In a point, x comes before y. But in this one, it doesn't matter. And the last thing, sort of well-defined sets. In order to be well-defined, a set, you have to be able to determine what is in and what is not in the set. And when we go on to the next section, we'll sort of use well-defined to say that we have to define the universe from which we are pulling out these sets. But for now, let's just consider two examples, one that is well-defined, one that is not. The first one, if I do this and say, okay, let's make P over Q like our rational numbers, such that Q is not equal to 0. And this right here is what most people try to say for rational numbers. It's a fraction where the bottom number can't be 0. But it's not clear where P and Q are coming from, or from where P and Q are coming. They could be integers, which would, if I said P and Q had to be integers, this would be our rational numbers. But they could be real numbers. They could be complex numbers. They could be colors. They could be words. They could be symbols. It's not clear. It's not well defined. So let me put that down. Not well defined. However, if I'm explicit with where these are coming from, like our full example of rational numbers, P over Q, such that P and Q are elements of the integers and Q does not equal 0. Then we have a well-defined set. We know exactly what is in and what is not in the set.